Shifting is one of the most essential tools in signal processing. Left or right, continuous and discrete. Delay or advance. Just theory? Or widely used in real systems? Let's understand time shifting. Hello, and welcome to Signal Space. Welcome to our first deep dive into signal operations. Time shifting, the foundation of signal analysis. Let's take a quick look at the key operations performed on signals. Every signal is defined by two core components, the independent and dependent variables. First, we have transformations of the independent variable, usually time itself. Next, operations that modify the dependent variable, altering the signal's amplitude. And some operations transform both variables simultaneously. These are the fundamental operations for transforming the independent variable. And these are the different ways to manipulate the dependent variable. And these are the popular hybrid operations that transform both variables simultaneously. Let's begin with time shifting. Mathematically, t is replaced with t minus the shift amount, say t0. Visually, this results in a physical displacement of the signal along the time axis, moving it either forward or backward. Let's consider an example where the shift quantity is positive, say 3. We'll define our new signal, x of t minus 3, and evaluate its values across a broad range of time, since we don't have an idea which way the signal is going to move. If we start at t equal to -10, the shifted signal requires the value of the original signal at t equal to -13. Checking our original signal, this falls into the 0 amplitude zone. This remains true until we reach t equal to 2. At this instant, we need x of -1, which is 5. This amplitude holds until t equals 4, after which it returns to 0. By mapping these points, we see a clear transformation. The original signal's range from -1 to +1 has now shifted to the new interval of 2 to 4. Visually, the transformation is clear. A shift of +3 results in a 3-unit time delay for the entire signal. Now, what if the shift quantity is -3? By performing the same computation, it becomes clear that the original signal range of -1 to +1 is transformed into the interval of -4 to -2. Visually, the entire signal has shifted to the left, representing a 3-unit time advance. The same principle applies to discrete time sequences. Here is our original sequence and its delayed counterpart. And when the shift amount is negative, the sequence is advanced in the time index. Notice the sequence representation during a delay. The entire sequence shifts right relative to the origin marker. Think of it as a relative motion. To perform a delay, you can either shift the sequence right or translate the origin marker to the left. It's a faster way to re-index the sequence. Similarly, for an advance, you can either move the whole sequence left or shift the time origin marker to the right. Let's make this concept clear with a few more examples. Consider the signal defined here. First, we'll look at its graphical form. And here is the result of a 1-unit delay. If we push the shift to 4 units, notice how the signal is translated deep into the positive time axis. Now, reversing the direction, a 3-unit advance pulls the entire waveform to the left. Looking at this family of shifted signals, the relationship becomes evident. The sign and magnitude of the shift dictate exactly where the signal lives on the time axis. Let's observe the discrete case. With the original signal as our reference, we can clearly see how different shift values re-index the sequence samples. Now that we have finished the theory of time shifting, let's look at a real-world application. Suppose there is an unknown object we want to track. We can use a pulse transmitter which sends a specific pulse toward the object. The pulse gets reflected back by the object. Our transmitter system is also equipped with a pulse detector and signal processing unit, which computes the delay between the transmitted and received pulses. Then, with the help of some basic mathematics, the distance of the object can be accurately determined. If this is done continuously in sequence, the speed and direction of motion can also be found. This is the principle used in radar and other ranging systems. Let's have a look at another example. Most communication systems suffer from echoes, where the received signal is a combination of the actual signal and its delayed versions. This happens mainly due to multipath propagation caused by reflection, refraction, and scattering. As a result, the quality of the received signal gets degraded. Suppose a source is sending a signal to a receiver. If they are in line of sight, one copy may travel through the direct path. At the same time, a reflected copy of the same signal may also reach the receiver with a delay. This delayed copy is called an echo. So the received signal becomes a combination of the actual signal and its echo. If the exact delay of the echo is computed, an estimate of the echo component can be obtained. This can then be subtracted from the received signal to remove the echo. This is the basic principle behind echo cancellation systems, which can be implemented using different algorithms. These are just some of the powerful, real-world systems that rely on signal shifting for their operation. Thank you for following this lecture. If you have any questions or suggestions, please leave them in the comments. Subscribe to stay updated for more signal space content. Until next time, keep learning.